Gold is one of the strangest metals on the periodic table because several properties that would normally make a material impractical have made gold extremely valuable instead. It is soft, unusually heavy, easy to shape, resistant to corrosion, and visually distinctive. Gold has the atomic number 79, meaning that every gold atom contains 79 protons, and the element is represented by the symbol Au, taken from the Latin word aurum. Pure gold is extraordinarily dense. 1 cubic centimeter of gold has a mass of roughly 19.3 grams, meaning that even a relatively small gold bar feels surprisingly heavy when it is picked up. This high density has historically been useful for detecting counterfeits because most cheap metals simply do not weigh enough. If somebody made a gold-sized object from aluminium, for example, it would feel obviously too light. Copper is much heavier than aluminium, but it is still nowhere close to gold. Lead is denser again, but a lead object matching the dimensions of a genuine gold bar would still be noticeably underweight. For a long time, this created a simple problem for counterfeiters. If they matched the size of the real bar, the weight would usually be wrong. If they increased the size until the weight matched, the dimensions would become suspicious. Then there is tungsten. Tungsten is element number 74, represented by the symbol W. It is a gray metal famous for surviving extraordinarily high temperatures, and it has the highest melting point of any pure metal. Tungsten is used legitimately in industrial tools, high-temperature components, specialized electronics, and applications where hardness, density, or heat resistance are useful. The United States Geological Survey describes it as a dense metal with exceptional strength at elevated temperatures. For gold counterfeiting, however, one property matters above almost everything else: its density. Gold has a density of approximately 19.3 grams per cubic centimeter. Tungsten is approximately 19.25. The difference is so small that two objects with the same dimensions, one made from gold and one made from tungsten, can have extremely similar weights. This is the central reason tungsten appears in discussions about sophisticated fake gold. The similarity is unusual. Most metals are either significantly lighter or noticeably denser than gold. Tungsten happens to land almost directly beside it. The London Bullion Market Association, one of the major organizations setting standards for the professional gold market, specifically notes that tungsten's density is almost identical to gold's. Chemically and physically, however, the two materials are very different. Gold has its characteristic yellow metallic color, is relatively soft, and can be flattened or shaped easily. Tungsten is gray, extremely hard compared with gold, and behaves very differently when electricity or sound passes through it. Those differences eventually give us ways to tell them apart. But from the perspective of a simple scale, tungsten creates a problem. A basic fake gold bar is not particularly difficult to discover. A cheap metal covered with a gold-colored surface may look convincing in a photograph, but its weight, dimensions, electrical properties, or composition can expose it. Tungsten allows for a more sophisticated form of counterfeit. Instead of making the entire object from an obviously lighter material, fraudulent bars have been discovered in which tungsten forms part of the interior, while gold remains on the outside. The external surface can therefore look and behave like gold during a shallow examination, while much of the expensive material that should exist inside has been replaced. The important point is not the exact construction of these bars, but the principle behind the deception. A genuine gold bar gets much of its value from material that you cannot see. Replacing some of that invisible interior with a much cheaper material creates a large difference between what the object appears to be worth and what it actually contains. With a low-density substitute, the deception immediately changes the weight. With tungsten, it may not. Imagine a simplified bar that should contain a certain volume of pure gold. If that entire volume is gold, its mass follows directly from gold's density. Replace part of the invisible interior with copper, and the total mass falls significantly. A sufficiently accurate scale combined with measurements of the bar can reveal that something is wrong. Replace part of it with tungsten, however, and the mass changes by a much smaller amount. The bar can potentially remain close to the expected combination of weight and size. That is what makes tungsten counterfeits interesting from a physics perspective. The counterfeit is exploiting one property that the two elements happen to share, while depending on the buyer, not checking the many properties in which they differ. Weight is therefore useful, but it cannot prove that a bar is genuine. The same applies to dimensions. Professional bullion products are manufactured to controlled specifications, so measuring length, width, thickness, and mass can catch many bad counterfeits. But if the substitute material has nearly the same density as gold, passing those checks becomes possible. Another familiar test involves magnets. Pure gold does not behave like iron and will not strongly stick to an ordinary magnet. If something sold as gold is strongly attracted to one, that is an obvious warning sign. But the opposite conclusion does not work. A bar failing to stick to a simple magnet does not prove that it is gold, because many other materials are also not strongly magnetic. Tungsten itself has only a weak magnetic response, so the magnet test is not a complete solution. LBM material discussing counterfeit coins specifically notes that tungsten-based fakes require more careful examination than ordinary low-density substitutes. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. You might then try testing the surface chemistry. One professional technology used for precious metals is X-ray fluorescence, usually shortened to XRF. The instrument directs X-rays toward the material and analyzes the characteristic radiation emitted by the atoms. Different elements produce different signatures, allowing an instrument to identify gold and estimate the composition of the tested region. This is extremely useful for checking metal composition, but there is an important limitation when the problem is hidden inside a thick bar. A surface measurement primarily tells you about the material being examined near the surface. If the exterior is genuinely gold while the suspicious material is deep inside, another technique may be necessary. That technique is often ultrasound. Ultrasonic testing sends high-frequency sound into the bar and listens for the reflections. If the material is consistent throughout, the signal should behave in a predictable way as it travels through the object and reflects from the opposite surface. If there is an unexpected internal boundary, cavity, or different material, an additional reflection may appear. Even better, sound travels through gold and tungsten at very different speeds. The LBMA states that there is roughly a factor of 2 difference between the speed of sound in gold and tungsten. That means tungsten may imitate gold extremely well in density, but it does not imitate the way gold carries an ultrasonic wave. This is an important pattern in authentication. A counterfeit may copy one measurement. It becomes much harder to copy several independent physical properties at the same time. Professional testers can therefore combine mass, dimensions, surface analysis, electrical measurements, and ultrasound rather than trusting one magic test. If the weight is correct, check the dimensions. If the dimensions are correct, examine the material. If the surface is correct, test deeper into the bar. The objective is not to find one characteristic tungsten shares with gold. It is to find a characteristic that it does not share. That is why sophisticated bullion markets use multiple layers of verification. There is another layer that has nothing to do with atomic physics at all: provenance. Professional gold bars are not supposed to be anonymous yellow rectangles. In established bullion systems, markings can identify the refiner, fineness, serial number, and production information. Under current London Good Delivery specifications, recognized bars carry identifying marks including the refiner, assay information, fineness, serial number, and production date information. Those records create a chain of trust. A serial number does not make counterfeiting impossible, because numbers and logos themselves can also be copied. But a number that does not correspond with legitimate records, markings that do not match the manufacturer's normal design, or a bar appearing in circumstances that make no sense can expose a fake before advanced scientific testing is even required. And that brings us to the black market behind fake gold. There is no evidence for one enormous secret organization producing every counterfeit gold bar on Earth. The reality is much less cinematic and much more fragmented. Counterfeit bullion ranges from crude objects made from cheap materials to far more convincing products designed to imitate legitimate refiners. Some scams happen through private sales and online marketplaces. In Australia in 2024, for example, ACT policing investigated counterfeit bullion sold through Facebook Marketplace. Victims were shown fraudulent receipts supposedly proving that the bars came from the Perth Mint. Independent appraisal later found that the supposed bullion included copper and gold-plated plastic rather than genuine gold. That particular case is important because it shows that tungsten is not necessary for every scam. Many victims are not defeated by advanced metallurgy. They are defeated by convincing packaging, fake paperwork, a familiar logo, an attractive price, and the assumption that something which looks professional must be genuine. At the more organized end, fake gold can become part of international fraud networks. In February 2026, the FBI announced arrests connected with what it described as a sophisticated organized crime group based in Hungary and Dubai that was selling fake gold bars to investors. Investigators said they had identified around 400 victims in New Jersey with losses exceeding $1.5 million. The FBI announcement establishes the reality of organized counterfeit gold schemes, although it does not say that those particular bars use tungsten. That distinction is important. Stories about tungsten gold have sometimes grown into claims that enormous quantities of supposedly legitimate central bank bullion are secretly fake. The available evidence does not support treating those claims as established fake. The LBMA says examples of tungsten inserts have been discovered in small bars, but states that they have never been discovered in the large bars held within central bank vaults and the London good delivery system. So tungsten-filled gold is real as a counterfeiting technique. But that does not mean every dramatic internet story about fake national gold reserves is real. This also explains why major bullion markets put so much effort into maintaining a controlled chain between refiners, vaults, traders, and buyers. London good delivery bars are roughly 400 troy ounces each, with formal requirements covering weight, purity, physical appearance, and markings. Refiners must meet standards before their bars enter that system, and vaults can reject bars that show suspicious physical characteristics. Ultrasonic testing became common in London vaults partly because of concern over exactly this type of adulteration. According to the LBMA, most London vaults installed ultrasonic equipment in the early 2000s as concern grew around the possibility of tungsten inserts. The response to better counterfeits, in other words, was better verification. For an ordinary buyer, identifying suspicious gold should follow the same principle, even without access to a bullion vault. Start with the things that can be checked without damaging the object. The stated weight and actual weight should agree. The dimensions should match the manufacturer specification. The logo, typography, serial number, packaging, and other markings should be consistent with genuine examples from that refiner. Obvious discrepancies are reasons to stop treating the item as authentic. But none of these observations alone can certify a suspicious bar. A convincing counterfeit may deliberately reproduce the easiest features to inspect. The next step for anything valuable is professional verification. A reputable bullion dealer, refiner, or precious metal testing service can use multiple non-destructive methods rather than relying on appearance. Surface composition can be compared with deeper measurements, while ultrasound can reveal internal structures that a scale cannot. For particularly valuable material, professional assay or refinery testing provides much stronger evidence than home experiments. The safest principle is simple. If the authenticity of an expensive bar matters financially, do not try to prove it using one internet trick. Use independent measurements. This is ultimately why tungsten is such a fascinating counterfeit material.